Dr. B, your chemistry teacher, and today we are going to be discussing preparation of oxygen. Preparation of oxygen. But very importantly, what is oxygen all about? Of what importance is oxygen? Now, oxygen is used every day. You might know because you use oxygen in respiration. I hope you know that what you take into your body is, your lungs is oxygen, and what you give out is carbon dioxide, which is also of help to the process of photosynthesis where plants have their food being synthesized. Now, oxygen is also very good and very important in combustion. I hope you know that without oxygen there is no combustion, and that is why when there is heavy fire, you cannot quench that fire just by pouring water, ordinary water, into the fire, because it increases the amount of oxygen instead and allow for combustion. No wonder the test of oxygen is by you putting off a light and allowing only the glowing splint, and you use that glowing splint into where there is oxygen gas, and you're going to have the splint turn up with flame immediately. And once you remove that particular flame, it goes off now because it lacks oxygen. So where there is no oxygen, combustion becomes very, very difficult. And oxygen can be used in the hospital too. You know, when people have problems in breathing and they are taken to the hospital, they are being assisted with the use of oxygen. Now, oxygen can also be used in very different way, even in your welding process. What you use in the welding process is also part of oxygen. Now, a lot applications of oxygen are there, but today we are not talking about that. Today we are looking at how we can prepare oxygen in the laboratory and also in the industry. Two things: how to prepare oxygen in the laboratory and how to prepare it in also in the industry. But let us put down a diagram that will guide us in the laboratory preparation of oxygen. Now we have a diagram of this nature. So this is a clamp, this is a clamp, and this is a test tube, and this is a test tube. Okay, this is a test tube, this is a light heat rather that comes in, and then down here we have a delivery tube that deliver the gas down here. Okay, so this continue in this format and this. Okay, so we have this out this way. Okay, now this is a very simple diagram that explains the preparation of oxygen in the lab, and this of course is your desk. So in here we have something of this nature. Okay, in here, and this is actually potassium trioxochlorate, chlorate 5, and then plus manganese oxide. These are the two things that are inside here, and this of course is your burner, which of course is your burner, and this is heat or flame, as the case may be. This is more like a measuring cylinder. Let us use this as a measuring cylinder. Okay, and then this is a rector stand, or a clamp. Okay, let us rather use this as you can probably do that with a conical flask, okay, or you can do it with any other form, any other thing. I use a conical flask and conduct this. You can use and this way here, this of course is your measuring cylinder. Okay, that's a measuring cylinder, and this is your delivery tube. Okay, inside here is Inside here is your oxygen gas, okay, and then this is the oxygen molecules coming out as air, and this is here, and here is water. Okay, so this is how it looks like. Okay, so this is how it looks like. So you can possibly have this kind of a diagram to explain how the how oxygen of course is prepared in the laboratory. Okay, so the very first way you can prepare oxygen in a laboratory is simply by the thermal decomposition of potassium trioxochlorate 5. Okay, this is potassium trioxochlorate 5. Of course, the 5 is the oxidation state of chlorine in this compound. So potassium trioxochlorate 3 is used when thermally means you apply heat. So when you apply heat to it, it's expected that it is going to break down, and when it breaks down, that must be done in the presence of a catalyst. This manganese dioxide is a catalyst. Okay, so this is a catalyst, and of course you know what a catalyst does. A catalyst simply helps to do what? To alter the path of a reaction. I don't want to use the word speed up a rate of a reaction, no. So the catalyst will help to alter the path of the reaction so that the reaction will be fast enough and oxygen will be produced. Now oxygen is collected over water. Of course you know that oxygen is quite lighter than water, so you can actually collect oxygen over water. And this is a test tube. Let me use this word, test tube. So this is a test tube. So this is a simple way of preparing oxygen in a lab. Okay, if you want to use the thermal decomposition of potassium trioxochlorate 5 in the presence of manganese dioxide as a catalyst. So this is a simple approach to preparing that. Now, in the second way you can also prepare this particular oxygen in the lab is by the decomposition of hydrogen peroxide. You know what hydrogen peroxide is used for? A lot of people use hydrogen peroxide for precipitation, especially when they have cuts, injuries, wounds, or something, bruises. So they use hydrogen peroxide to precipitate deaths. So hydrogen peroxide can also be used in the lab for the production of oxygen. And this is the sure way for laboratory preparation of oxygen, because in this way you do not really need, there is no much of accidents expected, and there is no much of troubles trying to create oxygen gas. So once you use hydrogen peroxide, still in the presence of manganese dioxide, you'll be able to produce oxygen. Again, you can decide to use potassium chromate. Okay, you can use potassium chromate. Potassium permanganate as your catalyst. If you do not want to use manganese dioxide for the preparation of your oxygen through the use of hydrogen peroxide, you can decide to use potassium permanganate. Okay, so to prepare that. Now there are equations that govern this, and we're going to put down the equation to see what happens around here. What is the nature of the equation that actually results to the oxygen preparation? So the equation for this kind of a reaction where potassium trioxochlorate 5 is used goes like this. So you have potassium trioxochlorate 5 in the presence of heat with manganese dioxide as a catalyst. You are expected to have potassium chloride plus oxygen as gas. Now you balance the equation. This will be 2, and this will be 2, and this will be 3. So with this, you have balanced the equation. So this equation is what it brings about this process. As soon as you set up this process for the preparation of oxygen in the lab, this is the equation that governs it. So 2 moles of potassium trioxochlorate in the presence of manganese dioxide as catalyst with heat present or introduced will give us potassium chloride and 6 molecules of oxygen, as the case may be. Now, in the second one, remember that we had mentioned something like using hydrogen peroxide. Okay, so if you decide to use hydrogen peroxide, then it means that hydrogen peroxide, this hydrogen peroxide, okay, in the presence of manganese oxide, will give you water and also give you oxygen as gas. Okay, so if you decide to use that, if you decide to use hydrogen peroxide, so you can balance this equation because here we have oxygen is 2 this way, that makes it 4, and 2 and 4. All right, so you can have this. So with this, you can also produce oxygen. So in the lab, to produce oxygen is in 2 ways, majorly. One, use of potassium trioxochloride 5 in the presence of manganese dioxide as catalyst, or you use hydrogen peroxide in still the presence of manganese dioxide, or you can decide to use potassium permanganate as the catalyst in your reaction. So these are the sure ways you can be able to produce oxygen in the lab. How about producing oxygen in the industry? What happened? Now let us look at how oxygen can be produced in the industry. Now this method can also generate the production of oxygen in the industry, except that you must mind the amount of heat you are using right now, the amount of catalyst you are using right now, and the preparation environment, because in an industry it requires a larger volume of oxygen to be produced. So let us look at how oxygen can be produced in the industry. Okay, in the industry. That is industrial preparation of oxygen. I must say that to produce oxygen in the lab, you can either produce it by electrolysis of water or by simply fractional distillation of liquid air. 2 things. So you can either produce it by what? Electrolysis of water, okay, where water is decomposed to give you hydrogen plus oxygen, 2 and 2. All right, so you can simply produce oxygen in this way by simply doing what? Breaking down water, electrolysis of water. But the major process that we use in the industry to produce oxygen is the fractional distillation of liquid air. Okay, so fractional distillation of liquid air. Now that is it. So always remember that if you are preparing oxygen in the industries, either by electrolysis of water or by fractional distillation of liquid air, or even by liquefaction of air. So by liquefaction of air, you can also produce oxygen. But the major aspect, the major procedure is in a fractional distillation of liquid air. How does it work? Now, let me first and foremost put down a diagram that will guide us on how it works. Now, let us look at this kind of a diagram that comes in. Now, we have this kind of a diagram, and this brings us to another chamber. Okay, we have another chamber. And this chamber brings us to this chamber, and this chamber takes us to another chamber. Okay. Compress, cooling. Okay, so it brings us to this other chamber here. Okay. And then, okay, we have this. And this chamber has something here that we have okay, so we have this. This is a typical fractional distillation column in the production of oxygen in the industry. Now, here you have, you said it is the fractional distillation of what? Liquid air. So here you have air coming in. This air is not liquid air. Now when this air gets into this chamber, this air is compressed and heated. Okay, so this chamber 1 has to do with compressing air and heating. Okay, so you have the air that comes into this first chamber is compressed. That is why you have this. So it is compressed and heated. Okay, when it's compressed and heated, it needs to be cool and then turned into a liquid form. So at this chamber that we have here, we have this. Okay, now what enters inside here? What enters inside here is nitrogen gas. So as this air enters here, it cools. It is cool. So at this second chamber, at this chamber 2, okay, so this air, the hot air, is cooled. Okay, so the hot air is cooled by the presence of the nitrogen gas that goes in. So the hot air is cooled, and as the hot air is cooled, what happens is it moves, transfer into the third chamber where we collect the liquid air. Okay, so this chamber, which is the third chamber, is collection of what? Of liquid air. You see? So we collect the liquid air at the third chamber and allow the liquid air to move into this chamber, which is the fourth chamber. And what happens in the fourth chamber is that up here is gas, nitrogen gas, and down here is liquid, is the oxygen in a liquid form. All right, so you have, here is your okay, let me put it this way. Here is your liquid oxygen. Now oxygen in this form is liquid. Now at this particular chamber where this is nitrogen gas collected, this is oxygen collected in a liquid form. Now when this oxygen is collected in liquid form, it will have to undergo another further heating that will now transform it into gas, into the oxygen gas. So in the industry, when you want to prepare oxygen, it's quite a lengthy problem, quite a complicated problem, especially if you're using fractional distillation of liquid air. So you get the air into these chambers where it is compressed and then heated. Perhaps the heating that is done here is to get some of the gases that have low boiling point out of the system, and then this air that is heated will come down to the second chamber where it is cooled. And know that once air is cooled, it will turn into liquid, and the nitrogen gas pumped into this chamber allow the air to be cooled, and of course it goes also mixing up with the air, and then it leads to the third chamber where the cold air is collected as condensed air into what? Liquid oxygen. Now at this particular point, it is going to move into the chamber where the nitrogen that is lower in boiling point of about 190 degrees Celsius to 195 degrees Celsius is collected in this form, while the liquid oxygen is collected at 185 degrees Celsius, and further heating is going to transform it into oxygen gas. Now in today's class, we have been able to discuss how we can prepare oxygen laboratory by simply thermal decomposition of potassium tetraoxochlorate 5 with potassium permanganate, and then we also discuss how we can prepare that in laboratory using hydrogen peroxide, still with what? With potassium permanganate or potassium manganese oxide, sorry, or potassium permanganate, as the case may be. And then in the industry we have also discussed that we can prepare by using liquefaction of air, or by simply electrolysis of water. But most importantly, that the preparation using or through the this fractional distillation of liquid air is the most available, most important aspect of preparing oxygen in the lab. I'm sure you enjoyed today's class and you learned something important from preparation of oxygen, both in industry and also in the lab. Do not forget to share this class. Do not forget to like, comment, and when you share, tell your colleagues and friends to do what, to also subscribe. Is free, so that they can get previous lectures and the lectures that will be popping up on their screen. There is also a Facebook part, Facebook part of these particular classes that we do here. Dr. B chemistry classes. Go there, share, and ask your friends to follow. And once they do that, they will get these classes as they come. Let them like and comment. Leave your questions in comment section, and I will attend to them. Until next time, it is bye for now.